A woman in her car, starting from rest, accelerates at a constant rate of 2 meters per second squared for 15 seconds until reaching a certain speed, and then continues to drive at that constant speed for an additional 15 seconds. So let's draw this problem out as two arrows, one arrow representing the time when she was accelerating, and then another arrow representing the time when she was moving at the constant speed. So for the first arrow, because she's accelerating, we're going to have to use kinematics, one of the kinematics equations. And for the second arrow, because she's moving at constant speed, we're going to be using the constant speed formula, v equals delta x over t. So in part A, we're going to calculate the total distance covered by the woman during the full 30 seconds that she's in motion. So we have to calculate the distance for each of the two parts separately, and then just add them together. So under the first part, let's just list all the variables that we know. It says she starts at rest, so VO is equal to 0. She has an acceleration of 2 meters per second squared, so A equals 2. The time was 15 seconds, so T equals 15. And we're looking for the distance that she moves in that first part. So delta x equals question mark. And you can see that the final velocity is the missing item here. So we're going to use the third kinematics equation. Delta x equals VOT plus 1/2 AT squared. Since the initial velocity is 0, we can get rid of that part of the equation. So we just have delta x equals 1/2 AT squared. And we don't even need to rearrange this because the delta x is already by itself. So it's just going to be 1/2 times a, which is 2, times the t squared, that's 15 squared. The 1/2 and the 2 will cancel out. So you're just left with 15 squared, which is 225 meters. So that's how far she goes while accelerating. Now let's look at the next part of the problem, the constant speed. We know that the time she spends moving at the constant speed is 15 seconds, but we don't know what that constant speed is, and we don't know what that distance is. So for right now, it's kind of hard to use this formula, v equals delta x over t, because we only know one of the three variables. So we're ultimately trying to find the delta x, the distance. So delta x is equal to v times t. So that means we need to somehow figure out what this v is going to be. So we can get that by going back to the first part of the problem and figure out what her final velocity is, because it says once she reaches that speed, she then just continues at that speed. So let's go back to the first part and just add a v equals question mark to our list of things. Notice now that we have 3 known variables, but we really have a 4th known variable now because we already solved for 225 meters for the distance. So we have 4 known variables and 1 unknown. That means nothing's missing. So which kinematics equation can you use? Well, it turns out you can use any of the kinematics equations except for the one you just used, because the one that you just used doesn't have a v in it. So we can pick any of the 4 remaining ones, and no matter which one we pick, we would get the same answer for v. So because we want to be as lazy as possible, we're going to pick the first one, the nice easy one. V is equal to VO plus AT. The initial velocity is 0. So just plugging in, you get V is equal to 2 times 15, which is 30 meters per second. And that becomes this V right there. So delta x is equal to 30 times 15, which is 450 meters. So adding together the 225 meters and the 450 meters, we could say the total distance traveled, 225 plus 450, gives you a total distance of 675 meters for part A. Part B, in which direction does the woman's acceleration point between t equals 0 and t equals 15? So we're looking at this part of the motion. We drew this arrow going to the right, and because she's speeding up, you know that acceleration is always in the same direction as the velocity. So according to the picture we drew, it would look like the answer for the acceleration is to the right. But here's where you got to be careful. This is just how we drew the picture, but it never said anywhere in the problem exactly which way she is going. It never said specifically she is driving towards the right. For all we know, the problem could have been set up where she's driving at an acceleration going this way, and then moving at a constant speed in that direction, in which case the answer would be to the left. So because it never gave a specific direction originally, the answer to B is that it cannot be determined. So watch out for those kind of problems. They're really easy to get you. Part C. Is it possible that the woman could be accelerating at any time, at any point between t equals 15 and t equals 30 seconds? Well, it says in the problem that from this part of the problem, she is moving at a constant speed, but it does not say she's moving at a constant velocity. And we defined acceleration as the change in velocity over time, not the change in speed over time. So it is possible that she could be changing her velocity, but how could she be doing that if she's moving at a constant speed? Remember, velocity has a magnitude and a direction. The magnitude part is the speed, so she's not speeding up or slowing down, but if she was like moving on a curved path or something, she would actually be changing her direction. So in that case, that would be considered a form of acceleration. And we mentioned in the notes, that's called centripetal acceleration, which we're going to talk about in about a month's time. Okay, so now a child suddenly runs out in the road, 20 meters in front of the woman's car. After a reaction time of 0.2 seconds, the woman slams on the brakes. Calculate the magnitude of acceleration necessary for the woman to avoid hitting the child. So for this one, the total distance is, you initially think it's going to be 20 meters, but she has this reaction time of 0.2 seconds, which means she's going to be moving at her same speed for 0.2 seconds before even starting to hit the brakes. So for that initial part of the problem, we have to use the constant velocity formula. So rearrange it for delta x. Delta x is equal to v times t, and she was moving at a speed of 30 meters per second for a time of 0.2 seconds, and 30 times 0.2 is equal to 6 meters. So of that 20 meter distance that the child's in front of her, she's already lost 6 meters of it. So that means she only has, and just subtract them, 20 minus 6, she only has 14 meters left before she would hit the child. So now we want to use kinematics because she's going to have to decelerate the car pretty rapidly. Her initial velocity was the 30 meters per second. The distance, delta x, we just said was 14 meters, and she needs to come to a stop. So the final velocity is 0, and we want to figure out her acceleration. So notice that the t is the missing item, so we can use v squared equals vo squared plus 2a delta x. It's the fifth kinematics equation. And we know that remember the order to do this now is you have to plug in any zeros first. That's going to be your first step. So we know that v is equal to 0, the final velocity. So that being equal to 0, we can rewrite this as 0 equals vo squared plus 2a delta x. And then to solve it for a, we want to subtract the vo squared from both sides. So we have negative vo squared is equal to 2a delta x, and then divide both sides by 2 delta x. So the 2's, the delta x's will cancel out. So a is equal to negative vo squared over 2 delta x. Just plug in the vo for 30, which is 30, and plug in the 2 times 14 in the denominator, and you will get an acceleration of about, this is equal to negative 32.14 meters per second squared, which you can't really see that now, but because it's off the edge of the tablet screen. But So it's negative 32.14 meters per second squared, but it says calculate the magnitude of the acceleration. Magnitude does not include direction, so you would not put the negative sign in. You just put 32.14 meters per second squared for her acceleration. And now for the final part of this problem, it says suppose you have this car where it's a self-driving car that's equipped with sensors capable of detecting possible issues before they happen. So for this particular situation, the sensors detect the child moving toward the road 0.5 seconds before she would even run out into the road 20 meters in front of the car. So not only does the car have the 20 meters to brake, it also has a little bit extra distance because the car started braking 0.5 seconds before that point. So we're going to do the same thing as before and figure out how much distance the car had. The car started braking beforehand while moving at a constant velocity using the delta x equals v times t formula. Plug in 30 times 0.5 seconds, and that is 15 meters. So that's actually the answer to part E. Well, not entirely. That's part of the answer to part E, that she has the 20 meters of stopping distance plus this additional 15 meters more because the sensors detected this thing happening beforehand. So the total stopping distance in part E is 35 meters. And then finally in part F, so now we're basically going to go through the very similar calculation to what we did before. So this is one of the reasons to show why you want to rearrange equations first before plugging in the numbers, because if you plugged in the numbers first, you'd have to go through the whole rearrangement again. But the fact that we're going to use the exact same equation, the exact same formula, with all the exact same numbers plugged in, except the delta x, instead of being 14, is now going to be 35. So when you go through all the same process again to plug the numbers in, you get an acceleration this time. The acceleration is equal to negative 12.86 meters per second squared. So because it wants the magnitude, just leave off the negative sign. So 12.86 meters per second squared.